Live.
I don't know if I've ever been public before.
Yeah.
Well, they're going to put a little system.
Actually, I hope so. Because I told my wife I was going drinking. I found out that I was at an astronomy club.
Oh, heaven forbid.
Look at my image. There he is.
All you got to do is flip.
A lot of traffic.
We are live and enhanced.
You
I just
click
sent
on
him the
that
link, so-
box in the lower right there, the U
No,
box.
I wasn't going to come, but then the heat, I didn't know how to get onto this. I thought to myself, I'm going to be sitting.
Ripped my arm off and I wasn't on for about
Get
2 seconds.
frustrated. And I was just
Yeah, right.
Okay.
You know what I mean?
Yeah. I was wondering if you start doing a sharing Google
Yeah,
something so
100%.
that it gets together you and just sit on the computer.
Well, there's no point having a meeting if we're going to, I mean, at some point here, there's no point.
Yeah.
But then you miss out on all the.
I know, and it's also
The
fun.
homeroom chit chat.
It's also fun to watch
There
Dave
he is.
struggle with the computer.
Hey there.
All right,
We are live.
we are live. You are all set to go.
Excellent. All right. So let me try to do one thing quickly here. Let me try sharing my screen. And let's share this. Now, if I do this, do you still see it or no?
Yes.
Yes.
All right. Well, hold on a second. Now, do you see it? Did it change?
No.
No. Okay. That was a little bit too much to ask. All right. We'll work off of this just fine here. So what I'm going to be talking about tonight is about pre-processing your images. For those of you who are brand new to this, I'm going to try to step you through a little bit of really sort of why we do this and why we would actually care. For those of you who have been doing this for a good long amount of time, hopefully still there are going to be at least a couple of tidbits in here that, that you can pick up and be able to apply to your images. I'm going to go through a little bit of the theory on all of this, and then after that I'll step through some of the practical bits and trying to use this as to try to figure out how we can actually get the most out of our images. All right, so first off, I wanted to make sure that everybody really had a good idea as to what the heck CCDs are actually doing for us. I found this image on the web here. This is from Microscopy U, and I think it's a really, really good analogy for how our CCDs actually work. What they're doing, think of them really as just buckets. And you can think of then the photons that we're getting from outer space, from our targets here, as raindrops that are filling these buckets. So what we have on the top is we can sort of see a little image here in which you've got a whole bunch of raindrops coming down and filling up these little buckets. And then after some amount of time, you have a shutter that goes and stops the raindrops from falling into it anymore. And then we go through the readout process. CCDs are typically read out by having a little, think of it as an electronic conveyor belt that slides the one row worth of pixels here, one row worth of buckets filled up with water, slides it over, dumps them then into the readout registers here. And then along these readout registers, it's another little conveyor belt that then goes and dumps the intensity from one of these buckets or one of these CCD pixels into a sort of measuring container, and that's your analog to digital converter. It does it for the next pixel on that line, the next pixel on that line, the next one, the next one, the next one, and you read out pixel by pixel exactly what the intensity is. So areas of the sky that you're getting more photons from, brighter areas of your galaxy or your nebula, you get more filling up your buckets. Dimmer areas, you're getting less filling up your buckets. And so by this, remember, each bucket is just a pixel. We end up making up an image here. And really, this is what we're doing. It's actually a remarkably good analogy for how we actually form an image. Because we can take this physical analogy that all of us can understand and turn it into some of the details about how CCDs actually work. So for example, here in this diagram, you can see that there are a whole bunch of raindrops that aren't hitting any of the buckets. All right. Well, in the design of CCDs, they talk about the fill ratio. And what the fill ratio is really how big these buckets are. How much of the space do they actually take up? By the way, can I do any kind of drawing? No, okay, I can't do any kind of drawing. All right. So the fill ratio is how much that you're actually picking up. By the way, do you see my mouse?
Yes.
Probably not. No? Okay.
Yes.
Yes. Oh, okay, great. So you can see that then you have spots where the raindrops aren't hitting, so they're not filling this up. And so when you talk about a CCD that has a higher quantum efficiency or higher QE, that's typically because these buckets are physically bigger. When we talk about full frame versus interline transfers, this is actually diagrammed as a full frame. And so you're grabbing off one line at a time into their single readout register here. What happens in interline ones is that in between the buckets, there's a little thing that can hold the charge. You dump each one over, say, to the right into the interline transfer registers. They all go at once, and then it goes and reads them out. All right, well, it's going to take some physical space to have that. That's why those interline transfer ones have a little bit lower quantum efficiency than the full frame ones. This also shows why you need a shutter to be able to go across and stop the raindrops from coming in. In this style here, and in full-frame CCDs, if you didn't have that, as you're reading out the one on the far right here, you'd still be accumulating raindrops into the others. So you'd get a gradient to your image, which we wouldn't want. All right, so this analogy holds pretty well for this. It also, though, holds for all the different kinds of problems that we can actually have in our pixels. So if we think about this raindrop analogy, do you think that as it's raining down here, let's say it's an even amount of rain. Granted, in Southern California, we have a tough time knowing exactly what that is, but let's pretend that there's an even amount of rain. Do you really think that every single bucket would get the exact same number of drops? Probably not. You know, you get a little bit more in one, a little bit less in the other, and this sort of thing, and that's just like the shot noise that we get. Shot noise or photon noise is anytime you have a flux of photons coming in from your deep space object, or even just heat coming in from into your dark current here, you don't always get the same amount. Even though they may be coming in at 1 photon a second, it doesn't mean that in 5 seconds you're going to have exactly 5 photons. They come in at a little bit of an odd random rate. It follows something called a Poisson distribution, which has a fun history. A French surgeon on the battlefield was trying to figure out why sometimes he would get people who were kicked by a horse, and then the next day he'd get somebody kicked by a horse, and then it might be 5 days before somebody came in being kicked by a horse. He's a mathematician. He figured out this thing called the Poisson distribution that describes exactly that. But in any case, you're probably not going to get the exact same number here. There's going to be some variation in that. And that variation is the same kind of variation that we have in our photons coming in, and that's the shot noise. All right, so we go through, we dump all of these things, we dump it into the readout registers, then we go and we actually have it go into your analog to digital converter here. Well, if you were sitting there and you were trying to read off of the calibration marks on the side here, even if you got the exact same number each time, you might not always call it the exact same thing. I mean, if you've ever looked inside a beaker, if your eye isn't lined up absolutely perfectly, you're going to get a little bit of variation on there as you try to read off that measurement. Okay, that's read noise. Every time you read the image, there's some noise that's just injected into it. How about these buckets? Are they made exactly to be the same exact diameter perfectly and they're all perfectly round? Or are some of them maybe a little bigger than others? Well, if they were a little bit bigger than others, some of them would capture more drops than others. So some of them would be brighter in our image. All right, well, we have things like little bits of dust that sit on top of our CCDs, and that blocks some number of the photons coming in. Well, if a bucket here is a little bigger, if there's a little something stuck in front of it or something like that, again, it would block some of those raindrops. So that's why we have dust motes, and that's why we have vignetting, because there are things that are preventing those raindrops or those photons from actually going and ever making it to the buckets. All right, well, maybe it's humid here. We've got it raining, so there may be some condensation here. What if some buckets just kind of automatically fill up a little bit more than others because of condensation? Well, that would be our dark current. Okay, when we dump these things out, do you every single time get all of the drops to come out? Or maybe some of the buckets are a little bit greasier or some are a little stickier than others, and so they dump more or less of the total amount of water. That could be like our bias current. So in each of these, for each of these kinds of problems that we talk about, there are nice analogies that you can have in the sort of physical realm, something that we can understand perhaps a little bit better than the details of how charge transfers work inside of a CCD. And as I say, really the analogies hold nicely. So we've got all of these sources of problems. And our goal in pre-processing is to pull out as many of these problems as we can. And then in other bits of processing, it's to try to pull out some of the others. Okay, so in here, this is now just I'm going to start to step through with a couple of equations, and there aren't too many of them, but I did want to have a couple in here. I'm going to step through what goes into the intensity level that you actually get in any pixel, and so therefore what we can actually do to pull it out. So these are kind of what you might call the rules of the road. So one thing is that, okay, you open up your shutter and signal from the target builds up over time. So longer you have your shutter open, the more actual signal you're going to be getting from your target. Great. And here, by the way, target will encompass both your actual deep space object and also your sky globe. Well, okay, you've got your shutter open. Dark current is building up as well. We have heat. We're always going to have some amount of heat. And those are just still photons. They're in the infrared, but they can work their way into those CCD wells just like anything else can, and so that can build up charge into each one of our wells as well. Longer it's open, the more you build up. Bias. Bias is really just a constant bit that's added into the image. At least ideally, it's a constant bit that's added into the image. Now, I mentioned already in terms of the physical analogy, the optics, you could have things that are blocking the raindrops or blocking your photons a little bit more than others. So vignetting in your system or dust motes. They build up, that goes, and what this is doing is this is then actually filtering the target signal. So it's affecting the target signal that's going on here. So okay, as we start to then try to build up what our actual equation for what's going into our CCD pixel here, the equation starts to look just like this here at the top. It says total signal after a given time. It's going to be equal to a couple of components here. One, okay, look, you've got this target at that time. That's the key thing we're really going to care about, but it's scaled by whatever the optics are actually doing to it. So that's why vignetting is going to be cutting down some pixels more than others. But it's this target signal filtered by the optics, plus the dark signal, which is also a function of time, plus your bias, which isn't a function of time. That's just this constant that is added into it. But now all of these things here, all of these things have noise components associated with them. Each one of these signals, the target, your DSO, and your sky glow, the dark noise, and even the bias has a shot noise associated with it.
Hey, Craig.
Sorry, yes?
Yeah, I don't see any term in there for responsivity variation over the array, the pattern noise, because the responsivity over the detectors is different.
So okay, so in terms of the fixed offset aspect of that, that goes into the bias. You can think of that as really the optics. The responsivity differences here is really just another variant of the optic. So let's think about this in a more concrete analogy. In a one-shot color camera here, what you end up having is you have different color filters superimposed on each one. Some of those are going to be red, some green, some blue typically, and obviously those then have different throughput transmissions actually to them. And so since you have different throughput transmissions, you have different responsivities to it. All right, well, let's say then that some of those filters are manufactured a little bit denser than others, and so that's not a perfectly smooth thing. That's then going to lead, even within your red and within your blue, to different levels of the intensity. So whether it ends up being an actual optical thing that's cutting it down, or whether it's a gain difference inside the well, one well is a little bigger than the other or something like this, it's still going to be able to be modeled the same way. So this optics can be a little bit more general term there, because that's not affecting the dark current typically. Well, okay, in some cases it could affect the dark current, but all right. Fair enough. I could add something in here to multiply by the dark current to take care of that as well. Okay, so then other things that we have going in here is we have noise. All of this signal is subject to shot noise or photon noise here. And this is typically going to be a 1 over root, it's a Poisson kind of process, and so we're taking a square root of this here. In addition to the total signal causing this shot noise, you also have read noise. I mentioned this, just every single time you read something out, there is some amount that is actually added in here, just some amount of randomness that's added in here. One of the big points that I want to try to draw out in all of this, and it's something that sometimes gets people a bit tripped up whenever I give talks on things like signal to noise and trying to get the highest signal to noise and cleanest kind of images that you actually can. In all of this, we can try as best as we can to estimate the true value of the signal. We take 100 frames, 1,000 frames, something like this. We can try to estimate the true value of the signal. From that, we could figure out on average how much noise maybe was added into each frame. But the problem is we can't actually tell on a given frame, in particular a given new frame, what the noise component is. So we can estimate and remove the expected value of the signals, but unless you're omniscient, unless every time somebody flips a coin, you can tell ahead of time whether it's going to be a head or whether it's going to be a tail, you're not going to be able to actually subtract the noise. This is why we're going to end up taking many flats, many dark frames, and why you take many images to begin with, because this noise is unpredictable here. Let me try to give one other little analogy just to make sure that it sinks in for people. Because this notion of the noise, you know, as you stack it, everything gets clean, and so you think that the noise is truly gone. The noise is something we really need to be able to have a good handle on. So let's say that whenever you ask me some question, how tall am I? How much money do I make? What's in my wallet? Let's say every time you ask me the question, I come up with my correct answer, and then I lie. I add in or I subtract some amount because I don't want you to actually know the truth. Now, okay, that's not very nice of me, but look, there are systems, I mean, pretty much any system that you're talking about here, whether it's CDs or anything that's measuring anything, is always going to have some noise in it. Heck, you take something like a GPS system. You know, your GPS, we say, hey, great, it can locate exactly where I am. Well, no, it can't locate exactly where you are. There's noise in the system to begin with, but in addition, at least it used to be the case for the civilian ones, the satellites would automatically add a bit of noise so that you wouldn't be able to unscramble it and actually figure out precisely where you were. They dialed that way back not too long ago. So, but let's say that you ask me something like how much money I have in my wallet, I count it, and then I add or I subtract a little bit, and that's the number that I tell you. So you ask me once, I say I've got 12 bucks in my wallet. Another time, I may say I've got 10. The next time, I may say I have 15. Now, if you keep asking me over and over and over again, ask me 100 times, you may be able to then say, okay, on average, across these 100 times, it comes out to be about 13 bucks. Sometimes more, sometimes less, but the average is 13. So you have a pretty good estimate of the true value, pretty close to it, assuming that I'm using a nice random number generator that, you know, and as I come up with my lies here. So now, instead of me lying about how much money I actually have, let's say that it's the dark current. Now, because we all want to be able to do things like subtract out the actual dark current from every pixel here in our CCD. And so if I say something like this, you know that on average, okay, we'll keep the numbers the same, on average the value here would have been 13 ADUs, analog digital units, coming off of my CCD. So now let's try to apply this to a light frame. You take some light frame, and let's say at that pixel the value is 100. So you know on average 13 of those counts, 13 of them come from the dark current. So you could pull it out and say, hey, the true value is 87. Sounds pretty good. But how do you know on that time that, well, when I lied, I added exactly 13? You don't. I might have added 13. So in truth, the real value may be 85 instead of this 87. And so that's then why we need to do multiple light frames, each one calibrated by taking out that expected value of 13. So this time it's 87, the next time it's 85, the next time it's 89, the next time it's 82, and we do a whole bunch of these, and it averages out to actually be the 87. All right, you can't pull out that noise in a single frame here. You just don't know how much of it was actually injected. You can pull out your best guess, the expected value, but you can't truly pull out the noise. Okay, so is that clear to folks?
Yes.
Yeah. Yes.
Okay. So let's now take a look at these equations here and just try to figure out again exactly what we're trying to do, and then we'll go through some of the ways in which we actually do it here. So your whole goal in pre-processing is to fix the problems in your image, fix these problems that have been associated with the CCD. Because again, on the top here, this total signal here, the only thing we actually care about is the target. We want to try to isolate this as best as we can. And so we want to try to factor out things like the dark current, the bias current, the optics, and yeah, and try to leave ourselves just with this. So then what we do is we take various control frames to try to estimate each one of these things here. So we'll do things like we'll say, okay, hey, look, let's take a dark frame. Let's take a dark frame that has the same exact duration as the target. And that'll give me an estimate as to, well, how much dark current is there. Maybe we take bias frames. I'll talk about when you do and when you don't take bias frames in just a minute. But if you take a whole bunch of bias frames, you can get a good estimate at each pixel as to, well, how much bias current is there in that pixel. You take your flats. Your flats here are done typically with a pretty short duration. A short duration, so this dark current doesn't really matter. But then biases are done with a short duration as well, so this dark current doesn't matter. And you take it of a nice smooth thing. So you get to then have an image as to what effect the optics are actually having on your signal here. And since we can only try to, I mean, any individual read then has these noise components associated with it, well, we take a whole bunch of them to try to then average out this noise to then come up with our best guess as to what each one of these components are. Okay. So let's go through the different mechanisms in theory, and then we'll go through them here in practice here. Dark subtraction. This one has been around since the dawn of CCDs, and the earliest processing software had this built into it. And it's a simple set of equations that works because, by and large, CCDs are nice linear devices. Meaning that if you take something like your signals coming in from your photons from your target, and you add in some dark current, well, you take these two, you add them together, and the sum that you get is actually the sum of the two individual fluxes there. And since it's a nice linear system like this, we can subtract, we can divide, and we can do all these kinds of things to pull out the underlying components. This works and only works if it's a linear system. If it's gone nonlinear for one reason or another, well, the wheels fall off the cart and the whole thing stops working. So we take our lights. I mentioned already that your lights have these components to them. They've got your effect of the optics, sort of scaling the effect of the target. They've got the dark current in them, they've got the bias, and they've got the noise. When you say, okay, look, I'm going to cover over my shutter and I'm going to have darks. Well, obviously you don't have your target. That signal's gone to 0 because you've covered it over, but you get the dark, you get the bias, and you get the noise. When you take your flats, well, you're taking hopefully an even thing, a constant, while you have a nice flat panel or you put a t-shirt over your scope or something like this. So you're getting a constant times your optics. So you're getting an image of the optics here, plus the bias, plus the noise. So in your classic dark subtraction technique here, well, what you're ending up doing is you're saying, okay, look, let's take the lights minus the darks. And if you take the lights minus the darks here, you just take these two equations and you subtract them from each other. Well, the dark per nt goes away, the bias goes away, and the noise is still there because each one of these noises is a different noise, and so the noise component's still there. If you notice here, This is something that I have to correct people some good number of times on. They say, okay, look, hey, Craig, I used your software and I took a whole bunch of lights, I took a whole bunch of darks, I took a whole bunch of flats, I took a whole bunch of bias frames, I applied them all, and now I have all these weird things in my image, or the background went completely black, or something like this. Well, if you've done this, if you say the lights minus the darks minus biases, well, let's do, okay, forget this term here because that's going to remain dark minus dark, bias minus bias. The darks already have the bias current in them. If you then subtract the bias current again, you inject the negative, the inverse of the bias, back into your image, and so your image either goes completely black, largely black, has all sorts of weird noise in it, and okay, don't do it. If you're doing dark subtraction, don't collect bias frames, or certainly don't apply them in this way here. We want to be able to take care of the effect of the flats, and so it's the light minus the dark, the same thing, just scaling by the flats, and if you're being nice and clean, pulling off the biases, because your flats have both of these components in them as well. And in each of these things, you'll see that there are noise components still in both of them. All right, so this is the classic dark subtraction kind of equation, and honestly, it doesn't matter in the slightest what package you are using. Any package out there worth its salt should be able to do things like subtract and divide. It's not exactly complex math. A kindergartner should be able to, okay, fine, a kindergartner can do division, but really, you should be able to actually get this right here. And so there aren't actual differences in the packages when it comes to applying a classic dark subtraction sort of algorithm. Where we start to get a little bit weird and a little bit wonky is what is going on when the system becomes nonlinear. Because all of this is just a series of linear equations. That's that you can add them and you assume that it actually adds properly, it subtracts, it divides properly. There are some cameras that are decidedly nonlinear. In particular, the digital SLRs end up being decidedly nonlinear.
Greg?
Yes?
I have just a quick question about the flat. The flat doesn't contain the dark. Is that because of your flat, the light source is bright enough, so you don't need to worry about the dark?
Exactly. It's typically just done so quickly that the dark current is negligible. Now, technically, it's in there. But if you have a camera that inside of a quarter second or a half a second has appreciable dark current, get a different camera, man. Okay.
Hey, Craig.
I said a little bit in jest. Let me correct one aspect of that. If you're doing something like you're using a line filter, and maybe you're shooting the side of your observatory, and it's not exactly all that bright, and so you really have a 30-second kind of thing, you may want to start to think about the dark component inside here as well.
Greg, is there a reason why the font is different on those two yellow noise terms?
Yeah, because the noise is getting more and more complex as you're going through this. And so if we were to just have two constant things here, and we know that if we were to say that this is some Gaussian kind of distribution to the noise, I can say, hey, look, the noise is going to be 1 over √2 what it was before. However, if we take a look at what's going on here, let's say that you're really pretty stupid, and you take one flat frame. You say, hey, look, it's nice, it's bright, it's only 1/10 of a second. What's the big deal with that? Let me just take one flat frame. Well, that flat frame has read noise in it, and it also has shot noise in it from all of that bright light that's actually come in. You're dividing your light, your corrected light frame here, you're dividing that by this flat. So you're then scaling this noise disproportionately here. So any noise that you have in this flat gets scaled disproportionately into your light frame here. And so it actually becomes a pretty big problem if you've got very noisy flats. Try it sometime. Just take one flat and correct things, and you'll notice that your stack looks a heck of a lot worse. And so really the noise component here, it's getting more complex because we're doing things like we're doing the division and everything here, and also it can be getting larger. So that's why I stuck the noise here in a bolded kind of font. So, but that's why we collect so many darks. That's why we collect so many bias frames. That's why we collect so many flats here, is to try to get those noise components as low as possible so that we're not injecting them back into things. Because even when you talk about this here, this light minus the dark, if you have 100 lights, and that's great, but you're subtracting off just one dark, all of that noise that's in that dark, boom, that just got into every single one of your lights. Oops. So the noise can actually be going up as you're doing this processing. Since the noise can be going up as you're doing this processing, that's why some people, one of the reasons why some people choose the alternate method of bad pixel mapping. Because any noise in the darks actually gets injected into your lights. So that's why these guys get the color and get bolted there. Okay, so that's the classic kind of thing. There's a variant on this that uses some of the same components, but extends it a little bit, takes care of the darks in a different way. It's called bad pixel mapping. Bad pixel mapping, it's actually even now on some digital SLRs as a built-in kind of thing I've seen. It's in a whole bunch of different packages. I like the way it works in Nebulosity, and a number of folks have flagged it as being a particularly useful feature actually in there. But the basic idea is just a really, really simple one. Saying instead of going through and trying to go through pixel by pixel and estimate the dark current in that, most of the cameras these days, the dark current's really, really low. All you've got is you've got a collection of hot pixels, and maybe even some warm pixels. And if we could just find those, maybe you have, oh, I don't know, maybe you have 100 or 1,000 of them or something like this on your sensor here. If we can just isolate those and fix them, hey, we're done. We can apply a bias frame if we want. We can certainly apply flats and everything to the image. But all of that dark current kind of stuff is really only a problem in a select number of pixels for a lot of us. And so by going through and saying, all right, let me take a dark frame, or maybe a stack of dark frames here, and let me use that to generate this map, I can now go through and say, hey, let me actually fix just these pixels. And typically it's just done through an interpolation process in which the software goes through, looks at the neighboring pixels, ideally the neighboring suitable pixels. So if you're on a color filter array, it's not interpolating a red value from nearby green values. And so go through and then try to figure out what a good thing to fill in there is. And once you've got a whole bunch of frames, and typically there's a little bit of motion in between the frames, you'll never, ever, ever notice that, well, you interpolated and you filled in a couple of those values there. This is very useful, I've already mentioned, on CCDs, cooled CCDs with low dark current. Particularly if you've got one that isn't regulated. Let's say it does a really nice job, gets you nice and cold, but so there's not too much dark current, but you can't build up a great dark library because it's not regulated. Hey, apply bad pixel mapping. It can often work for folks a heck of a lot better. It's also useful on digital SLRs. Now, digital SLRs certainly aren't cooled, and in fact they have a whole bunch of hot or warm pixels. But here's why it's useful on digital SLRs. This technique, it's a sort of lukewarm pixel mapping technique that I don't know if he was the first one to do it, but he may very well have been. Chuck Kimball on the Yahoo group started really working with this with his Canon digital SLR, flagging a huge number of pixels, a good 5 to 10% sometimes even of the pixels on his CCD, flagging them as bad, and letting Nebulosity go in and fill in these values. And he was doing this because the dark current, at least on all of the Canon digital SLRs that I've tested, and I've tested a bunch of them, the dark current here doesn't follow a linear system. What happens when you open up the shutter is it's doing what it should be doing for daytime photographers here, or for non-astro photographers. It takes the image, and it shifts the histogram, and it stretches it a bit based on the amount of dark current that was in there. But unfortunately, we don't have a way to invert that and turn it back into a linear system. I first noticed this when I was doing a review of some digital SLRs, and I was trying to calculate the dark current. I would do things like open up the shutter for 1/10 of a second, calculate out the average value in the image. Now a second, now 10 seconds, 100 seconds, 500 seconds. And the bizarre thing was, whereas every other camera I'd ever tested, the intensity goes up the longer you have the shutter open when it's nicely covered over by a nice metal plate so that no light is getting thing. Kind of makes sense. In fact, it has to make sense. It has to go up. You can't possibly leave the shutter open for longer and have fewer dark current photons in your little CCD or CMOS well there. That can't be. And yet, what I found is the first camera I tested, actually the intensity went down as I left the shutter open longer. So the average background intensity in a 5-minute image was less than the average background intensity in a 1-second image. All right, something was going on. And what's going on is that Canon is shifting and stretching based, I believe, on some pixels called the optical black that don't actually get any light hitting them. And I think it's using that. I've yet to be able to crack the code as to what they're actually doing to pick that apart. So then if that's the case, if your light frames are actually stretched and shifted, if that's the case, then this isn't going to work, because it's no longer a linear system. Because throughout the night, the amount of heat buildup, the dark current, the stretching that's going on in your first frame is not the same as the stretching that's going on in your 10th frame or your 50th frame. And later on, when you go and you take darks, well, that's not going to be the same either, because the temperature is going to be different. People say, okay, hey, look, well, why don't we just do the built-in noise reduction that happens, where it takes a light and then it takes a dark. It takes a light and then it takes a dark. And it subtracts the dark that happened right afterwards, because that one, the temperature is going to be as close as possible, and so therefore the stretch will be as close as possible, and that's true. But then you're only using one dark frame to correct your light frame. So all of the noise that's in that dark gets injected here into the light. Now, it turns out that actually the Canon digital SLRs have very, very low read noise, and that's excellent. So that's why a number of people do that technique of still doing the alternating kinds of things. But still, all of the shot noise associated with it, all of that, well, you've still got all of that that's happening in there. But it does make for a more complex kind of system, and so that's then why actually a number of people have taken to using bad pixel mapping on digital SLRs here as well. All right, so any other questions so far on the theory on all of this?
Greg, is this only for Canon? I use Nikon. Do you know about the Nikon?
Honestly, I don't know about the Nikons. I bought a Nikon several years ago. I bought a D40X with the express idea of building in support for capture on Nikon digital SLRs in Nebulosity. And then I looked actually at their software development kit, and I realized it was different for every single Nikon. And of course, they come out with a new one every other month, which has a different software development kit. And just the routine to connect and take one test frame was twice as long as the entire Canon code, which was in itself 10 times longer than any other camera's code. And so at that point, I gave up actually working on the Nikons. So I haven't actually gone and done the testing on it. However, it's an easy thing for you to do. All you need to do is go and take a series of dark frames and calculate out the average image intensity in each one as a function of time here, and see, does it go up, does it go down, or does it stay the same? Yeah. Now, if it stays exactly the same or goes down, you know you've got the problem. If it goes up, well, you may or may not have the problem. There's another way you can start to look at it. It gets a little bit more complex. You've got to look at the standard deviation in there and see if the standard deviation is proportional to the mean. In every system like this, the standard deviation is proportional to the mean, or the variance is proportional to the mean. And in every camera I've tested except the Canon digital SLRs, it is. In the Canon digital SLRs, it isn't. So, but you should be able to do that kind of thing to get at that there as well.
All right. I don't know if it's a similar test you suggested, and then I didn't check the linearity, but it went up. But then the deviation wasn't like linear. So right. I need more tests to check it.
Exactly, and that's then where. So in one of my reviews, which you can get to off of my website, I actually stepped through looking at the variance associated in this, and so you can make a histogram of the whole. Of the whole image, or you can get some image statistics here to look at the variance or the standard deviation in the whole thing. And in one of the articles that I have on the Canon digital SLRs, I take you through then doing that variance versus mean plot. As an example as to why and how we know this has to be true, it's also exactly how you calculate out the system gain. you can actually calculate the system gain based off of dark current, because dark current is exactly the same. I mean, it shouldn't matter whether it's coming from infrared photons or visible wavelength kind of photons here. It should do the same thing. It does in other systems. It doesn't when it's gone nonlinear there. All right, so let's now turn to how one actually goes about applying this kind of thing in terms of using some package here. Obviously, I'm biased in terms of my package. For things like pre-processing, I only use one. That said, I don't mean to give the notion that I do anything and everything entirely in Nebulosity, and I make an image that is nothing but Nebulosity, and I will never have anything else but Nebulosity installed on my machine. And, well, no. I use other things. Of course I use other things. I use Photoshop. I use PixInsight. There are great programs out there. Photoshop you do not want to use for processing 100, for pre-processing of 100 frames here. I'm sorry. You'll die. All right. In Nebulosity 3 here, I tried to make the pre-processing steps initially look a heck of a lot more complex and freak people out, but actually end up being a heck of a lot easier and faster for everybody to process sets of images from a night here. So let me actually grab Nebulosity. Let's see if I can now shift my screen sharing over to here. There we go. And now let me actually step through a little bit of how we actually go about doing pre-processing here and why I think it's actually a heck of a lot better system than it used to be. And hopefully I'll get some feedback from folks that tell me, yes, that was great, I love that you did that, or here are 10 things that you could do that are a heck of a lot better than what you did last time. Either one I'll take. Okay, so let me see, do you get my menus as I do this?
No.
No.
No. Okay.
So you need to go back, as opposed to sharing the application, you really just need to share
the whole darn window. Let's just do that.
Yep.
Screen sharing. Let's share my desktop. You've got the desktop. We'll have an infinite recursion of you. I'll move you down here. All right. So then, okay, what are you laughing at? All right, so in any case here, let's go through and see what this is going to look like. So if I open up batch, because we're processing a whole bunch of things here, pre-process some image sets, this dialog comes up, and it is by far the nastiest looking dialog in Nebulosity. I typically try to have things that are nice and crisp and clean because I know when I am tired, I don't want to actually go and try to parse a whole bunch of stuff here. I try to think about the user interface, but this is one time where actually having everything in front of you makes a heck of a lot of sense. So let's step through what this actually looks like. So I've got some data here taken a couple years ago of the Crescent Nebula. And the reason why I picked this data here is that I've got a whole bunch of different, I've got RGB data, I've got line filter data, I've got all sorts of stuff on this here. And so let me try to show you what this would look like. So my RGB data, I can come back into this here. My RGB data is all 3 minutes on my QSI camera. Now I've gone through and I've already taken a nice library worth of shots here. So I have a control library, and I have things like, oh, okay, here's a 3-minute -10 centigrade library. I've already taken a whole bunch of frames and I've stacked them, and so I can say, hey, look, use that as my dark frame. Well, all right, I haven't always done that. Sometimes I do things like I take brand new darks or something like this, and so you can also say that, all right, what I actually have going on here too is I have some 10-minute darks because my line filter stuff is at 10 minutes. And so I can select a whole bunch of frames here, all of them if I want, and that becomes now dark number 2. So dark number 1 is this master 3 minutes. Dark number 2 are these 15 dark frames here. All right, let's see. Well, I've got some bias frames as well. I'm going to end up applying them to my flats. So here's a master bias. Again, you could have tossed in 1,000 bias frames if you want here. It's not going to matter. And, well, I took flats, of course, because flats are a good thing. So let's load up some flats. If we go into here and I say, all right, flats on the red, green, blue data, Let's grab all of my blue flats. There were 20 of them. Let's call set number 2 here, all of my green flats. And flat number 3 are all of my red flats. All right. So I've got some number of those loaded, and of course I had different flats for my hydrogen alpha data. So that's flat swept rotation line here. I've got a bunch of these. Now, if you're new, you may be wondering why I have flats for each different filter. I have flats for each different filter because, well, there are dust spots on the filters. And maybe they didn't center themselves actually perfectly, and so there's a little bit different vignetting. So, okay, flats are quick to take, so I just write a little script. It goes through the filter wheel. It takes all of my flats, and I'm done. All right, so we've loaded up all of these flats here. Now let's grab our light frames. And we'll come on into here. We'll go into red, green, blue. Let's say take the red frames. Let's grab, I'll clear something out here in just a minute. Let's grab the green frames. Light set number 3. We'll grab our blue frames. Yes, there is a nomenclature to all of these, but and let's also grab our hydrogen alpha line filter data here. I have multiple line filters, but in the purpose of time, let's just grab these. In fact, sure, we'll grab. Let's just grab night 2s in the interest of time. Okay. So I've now got all of these loaded up. In fact, let me do one quick thing here just to make sure that I, of course, like a good presenter here, I tested some things out ahead of time, and so I have some vestigial frames. Let me just get them out of the way so that everything is nice and clean and clear to everybody. And let me come on back because I think I also had some of the line filter. Yeah. Okay. So now then, I've told it all the things I want to be working on here. Nope, I forgot to tell. Apparently I overwrote my blues. So let me go back and get the blues in here. Apparently I just got some email. Okay, so now I've told it everything that everything I want to work on, but I haven't told it what to do, and that's why this dialogue is so big and nasty and hairy here. So for example, let's take our light number 1 here. Our light number 1, I want to apply a dark, and the dark I want to apply is this first dark here, the 3-minute one, because this is all my 3-minute data. I want the red, the green, and the blue to each have this one. This hydrogen alpha 10-minute data, I want that to have dark number 2, that 15, those 10-minute, the 15 at 10-minute ones here. My flats, what do I want to happen to my flats? Well, my flats here, well, geez, I might as well apply the bias. I have it, and that'll help reduce the noise in the bias. Since my since my flats were all nice and short, I'm not going to worry about dark current built inside them. It's a cooled camera. There really isn't any on that. And I also have this 3x3 median filter. I'm going to come back to this here in just a minute here. But let me take a look at my lights again here. This light, I'm applying this dark, I'm applying this dark. Well, of course, I want to apply the flats here as well. So in the red, let's apply the red flat, which happened to be flat number 3. I did this in a little odd order. This happened to be flat number 2. Hydrogen alpha here is flat number 4. And blue here is flat number 1. Okay. So when I hit OK here, what it's going to do is it's going to go through and it's going to pre-process all of these data sets according to what I've said. So it's going to say, OK, let me take this flat. Let me take these 20 individual flat frames. Let me average them together. Let me apply the bias frame, pull that out of it. And let me also do a little bit of noise filtering on it, a little 3x3 median filter. So it's going to slide a little 3x3 pixel window over everything, and it's going to take the median value of that. You have choices for 2x2 mean. You have choices for some Gaussian blurring, like 7-pixel blur, nothing, the CFA scaling. If you are shooting a one-shot color camera, you should either be using 2x2 mean, 3x3 median's not too bad, but 2x2 mean, or the CFA color filter array scaling here. 2x2 mean does a perfect job of stripping out the red, green, blue Bayer matrix. So that's what you should be using. That's the first pass you should think about. You can set a default, by the way, as to which one you like here the most. I, by the way, often use a 7-pixel blur. People ask why I do this. I do this to cut out the noise in the flats, because again, remember, your lights are being divided by these flats, so any noise inside here is going to get injected into the lights a whole bunch. I've never had a problem with dust motes having an odd kind of shape, having a little bit of a ring to them. If you're running at a very high F ratio, you may want to do something that's a little bit less blurry. If you're running at F10 or something like that, you're crazy, but you may want to do something like this. So whether it's a 3x3 median, a 7-pixel blur, something, it's going to help reduce any of the spatial noise. And up here, by the way, I'm saying that it'll be doing dark subtraction. You also have bad pixel options. So in any case, we've set all of this up. And yeah, it takes a minute or so to set up. But then here's the cool thing. I say, all right, this is all set up now. Go. So what it's doing now is it's processing the control frames. You can see as it's loading each one of these things up, I have the set it to auto stretch. So hey, look, I have dust motes. We all have dust motes. And so what this is doing is it's going through. Right now it's loading up all of the flats. It's on the blues. Then going to go hit all the other flats. And grand total, I timed this. Apparently these flats shouldn't be being used because they're too high. It's another thing, however, that you should. Here's a nice example of what not to do. Don't take your flats so that they're banging into the top edge. I should have picked a different set. Take them so they're more down here. Perfectly timed. Or here. Or here. Honestly, in fact, actually I was just asked this at a talk that I was giving actually by none other than Tony Hallis. He was saying, oh, where do you put it? Do you always try to keep it at exactly 30, or do you allow yourself to go to 50? As you can see, I allow myself to sometimes even go beyond 50. Okay, I should have filtered these out. But CCD cameras, even ABG cameras, are really nice and linear until you get up to at least 95% of the full well. Don't worry if your flat is down here or if it's all the way up here. As long as it's not banging into the top, feel free to use those flats. Okay, so I timed this before, and the entire thing, the entire calibration process, took all of 2 minutes. So okay, now it's gone in. It's stacked all of those. It's processed all of the control frames. So you can see here, processing, loading, processing, loading, processing, loading. Sorry, it's on the dark frames here right now. Why is this taking twice as long as it did last time? Must be the connection. So in any case, we go through here, it applies each one of these, it chunks through, and as I say at this point, you could have stepped away, go and grab a cup of coffee, but it takes all of about 2 minutes to actually go through and work.
Does Nebulosity use multi-threading?
So in many places, Nebulosity uses multi-threading. What I typically do is I benchmark it with and without multi-threading on my system. I've got a good number of cores here, and I'm running on an SSD drive, and if you get a benefit by multi-threading under those scenarios, I typically incorporate multi-threading. We're still on the pre-processing bits, however, we're often limited by the disk speed, and disk speed is not something that multi-threading is going to help you with at all. So actually, this routine here, I haven't multi-threaded, but most of the processing ones are multi-threaded. I must have told it to do a lot more this time than I was having it do in the demo one.
Hey, Greg, what does the 7-pixel blur do?
So what it does is after it's gone and it's stacked your flats, it just passes a 7-pixel Gaussian, just as if you did it in Photoshop or in the image blur tool here. It passes that over your flat, because your flat is going to have some grain to it. You can see here. See this grain in the flat?
Well, the question about the number 7. I mean,
oh, why 7?
5-pixel blur or a 6
Could have been.
Blur.
I experimented around to try to come up with something that is going to be able to take out the spatial noise, not just of a typical sort of read noise, but also some of the other things that you get, some of the patchy kinds of stuff that you get in in things like the digital SLRs. Certainly, if you have a color filter array, 7-pixel blur nicely still pulls out the color filter array, whereas if you go down to a 5mm or so, it doesn't. So it's arbitrary, but it's an educated arbitrary. It honestly doesn't matter. I mean, if you, I have people sometimes ask me, it's like, oh, okay, look, I mean, it's the same kind of thing like with the flats. You know, oh, gee, my average flat intensity was 35% instead of 33% of the maximum. It doesn't matter. It really doesn't matter.
7 by 7, is that the idea?
Say what?
Is it 7 by 7?
So it's a 7 mm radius, or 7 mm diameter. So it's a circle of 7 of a Gaussian. So a Gaussian is a bell-shaped kind of thing. So it's a round shape, and it passes that over the image.
Okay.
How did you get your CCD down to 273 degrees negative? Have you achieved absolute zero there?
I have achieved absolute zero, exactly. So that is a little bit of an in-joke here. It's a geek joke that I have for folks. If you don't have a camera connected, but you're asking to read it out, or if your camera can't read out the temperature, I spit out minus 273. It was either going to be that or it was going to be 42. So I thought minus 273 was more fun, at least for this here. Okay, so we've now gone through and it's processed every single one of these images. So that was 80 some odd images, passing in a whole bunch of individual flats, passing in a whole bunch of individual dark frames, and it's gone through and it's processed everything. And so in Nebulosity, what this now looks like is in each one of your directories, you have this pproc or preprocess underbar and then the name of the file that it worked on. You control that something else if you feel like. There was an option in the dialog to be able to do that, but that's the idea. If instead of using dark subtraction, if we wanted to do bad pixel mapping, all you need to do is say, let me make a bad pixel map. Do something like say, hey, let me find some dark frame that I've used before. Maybe let's take this master dark that I have. Loads up that master dark. And it says, okay, adjust your threshold. Let me make this a little bit bigger so that folks can see it. It says go and adjust your threshold. What it's showing you here is it's showing you the dark frame. And then as you adjust your threshold, do you see those little bright little dots come on?
Mm-hmm.
Those are the pixels that you're labeling as bad. In terms of how much of this you want to do, this is left as an exercise to the reader. So there is no absolute correct answer. Because look, each pixel has its own dark current buildup. Some of them build up almost instantaneously. We call those hot pixels. Some of them build up a little bit more slowly. We call those warm pixels. All right, whichever one you want to do in there, that's what you can set. As I say, Chuck Kimball on his Canon Digital SLR starts flagging, 5% or so of his image, or even 10% of his image as being bad. By the time you have a little bit of motion, a little bit of dither in between frames, however, you still actually get nice values built into there. Okay, so if you hit done, it asks you to save it. I won't bother saving it here. I already have a bad pixel map, and you can apply that in the same exact way that you would have done anything else. All right, so then at this point, we've gone through and we've taken a look at how the pre-processing sort of basically works here. And we've looked at how to actually go and make a bad pixel map. Very straightforward on both of them there. Now at this point, the next thing is, well, all right, you've got all of these. They've had a sort of very basic kind of correction stuck on them. What the heck are we actually going to do to make an image, and what are some of the tricks that you can pull in this to try to make some better images? Now, some of you may not know, some of you may know, that by day, I am not an astrophotographer. I'm not even a programmer for astrophotography software by day, or even a programmer by day. I'm a scientist by day. I actually try to figure out how memory works in the brain, and I do that by taking thousands of noisy pictures of people's brains. And the brain pictures that I take are sensitive to activity in the brain, and people move. So you have noisy images with motion, and you have to try to pull out what the true best guess as to the image, the activity in the brain was, out of these noisy moving images. And if that sounds a lot like astrophotography, where we're trying to pull out the true intensity image from noisy moving images, it's because they really are the same thing and the same problem. But I then come to all of this with a bit of a philosophy of, I sort of like to do no harm, do no evil to your underlying data, And so in all of this now, I always want to go through and be in control of what's going on in the processing, and I always want to also be able to see exactly what my data looks like. So one of the things when I grab my images, one of the first things that I do is I then load up this little thing, the preview tool. And let's go and take a look at some of these images that we've just made here, just to kind of show you what this looks like. Here are these pre-processed. I'm going to just grab right now, for example, the red frames. And I can say, OK, let's look at these things here. And so what it does is it's now loaded up the first of these red frames. I can slide my little slider to get a little bit better view on it. I can zoom in, I can zoom out, and I can see, OK, what does it look like? Am I getting anything? Hey, look, there's the Crescent Nebula. It's down there. Cool. All right, this looks like a pretty decent frame. I can go to the next one, and I can step through all of these and try to see, was there some bad tracking? Did my stars get all elongated in it? Did a plane go through the image? Because in fact, planes do go through your images. I've seen, let's see, I thought Red 10 had a plane go through the image, and we passed it there. Maybe Red 19 was the, two of them had a plane go through the image. OK, so here you can see there's actually something that went this way, probably a satellite, and here's a plane, and you can in fact see the lights. Here are the lights on the wings. There's the light on the tail. And so this is an image that I might want to say I don't care about. So you could do things like I could click on delete, and I could make it go away. But since I'm a scientist, I never, ever, ever delete data. I could just do something like I can say that this one is bad. And if I click on rename, what it's now done is it's now called this bad pre-proc red 3-minute frame number 19. And so you can go through and just manually check and see, hey, what do your images look like? Are there ones that you know you want to toss? And if so, label them as bad. You also have a little blink tool in this, so I can say, like, let's lock this one. Let's go to a previous one here, and you can do a little blink, and it blinks between them there. So nice to be able to detect a different. Oh, look, hey, there's another little thing. And another. No idea what those are. All right, but you can see those kinds of things with a nice little blink tool. All right, so you can do that kind of thing. And I typically just run through all of them, because you'll be surprised sometimes what you actually see. So for example, let's load up my hydrogen alpha data here. I happen to know in my hydrogen alpha data, I can grab the pre-processed stuff here. I happen to know, I'll tell you what, so in the interest of time, let me just grab the ones at the end and the ones at the beginning. OK, so let me change my little slider so I get a little bit better view of all this here. And hey, look, there's my Crescent Nebula. And so, OK, right now I'm looking at frame number 1. Let's look at frame number 2, frame number 3. Oh, that's frame number 18. Did you guys see how it got a lot brighter? Gets sort of a little bit washed out and bright. Yep. In fact, let me go back. Let me, I can lock this one, go next, and then blink. We can see that, all right, yeah, it got brighter because the sun was starting to come up. So if I wanted to, I could say, hey, look, throw away anyone that actually has this kind of increased intensity because the sun is coming up. But I mean, come on, these are 10-minute long hydrogen alpha frames. I don't want to throw away all of them. If the sun has totally come up and totally washed it out, sure, I'll throw it away. But this is still a reasonable looking frame. So we should be able to do something with this. Well, OK, as I say, I could go through, I could label it as bad, but let's see if we can actually do something about this. One of the ways you can do something about it is in the, let me get out of this now, is in the batch tool here, you have a normalize intensities and match histograms. Normalize intensities is kind of like the poor man's cousin to the match histograms. So let me use the match histograms here. And what this is going to do is I'm going to say it asks you for a reference image. I'm going to say, all right, that first one here in the night, that's going to be my reference image. And now what I'm going to do is I'm going to say, OK, let me grab, again, these pre-processed ones. Let's grab all of my hydrogen alpha data here. And now what it does is it loads up the reference image, looks at the histogram, and then goes through every other one and says, all right, what does my histogram look like? Let me make this histogram look just like the other histogram. And so this actually is using multi-threading. can see there was a little odd one there that we'll come to in a minute. This one actually is using multi-threading as it's trying to go through and actually do this. My CPU, oh, it's the Google Talk plugin. That's what's slowing us down here. All right, Google Talk plugin is taking 135% of my CPU. So that's why we're running slower. In any case, so what it's then doing is it's going through and it's stretching these to get it so that the histograms actually now match. So as this is just about finished up, I'll do that same kind of a blink sort of analysis here. Okay, it says it's idle, we're done. So now let me go into preview. Let's load up some images here. Let me do date modified so I can do this. Let me grab the 2 here at the end, and let's grab the 2 at the beginning. Okay, so let's now go, we'll again take number 1 here. I'm on number 1. Let's lock this. There's number 2. There's number 19. There's number 20. Let me do the blink. Okay, I've lost a little bit of contrast in it. You can see there's a little bit of motion, but that looks a heck of a lot better. So I'm going to be able to use the data actually from this other one here as well. The match histogram tool is a very, very important tool when it comes to things like standard deviation-based combines and all this sort of thing. And it can certainly save you in a number of situations. All right, so now that we've gone through, we've taken a look at some of these kinds of things. Let's actually go through and take a look at aligning these guys. So let's go through and let's say, all right, let's say do align and combine the images. Dialog comes up here, and there are a couple things to start thinking about first. One is, what kind of alignment are we talking about here? If you're trying to do something like make your own master library of darks or biases or flats or something like this, you don't want to use any alignment. You just want these things to go perfectly on top of each other. So that's no registration, no alignment, a fixed parameter. Most of you are just going to be using translation. Translation just means that the image shifts up, down, or left and right in between the frames, but that's it. If your polar alignment is decent, translation is going to be your way to go. Translation plus rotation starts to now get into, okay, if you're not well aligned, if you were taking things across different nights and they weren't perfectly lined up, you got close maybe, but not perfect, translation plus rotation becomes your friend. You use 2 points to help Nebulosity figure out what the rotation is. Scale. Let's say you're using an SCT, and as you adjust the focus knob, you actually are changing your image scale here a bit. All right, tossing in that extra parameter here is going to help here. I won't go into drizzle or colors in motion. There are different ways of actually then trying to do the same kind of image registration. So for this, my mount is lined up pretty darn well. I'm just going to use a translation kind of alignment. I'm also going to tell it to save each file. Instead of going through and saving a single file that has the entire stack, I'm going to save each file. And I'm going to show you why I'm going to do that in just a second. I also, by the way, I always do this star field fine-tune the alignment. All right. It now says, OK, what the heck do you actually want to do? Let's take these hydrogen alpha frames, tell it we want to do these, and fire them open. OK. If you haven't used Nebu, if you used it a long time ago, you haven't used it recently, this is a new dialog that comes up. What this is doing is it's giving you a little bit of a readout, letting you go through and edit your various alignment kinds of parameters here. So let me go through and just click on what it wants me to do now is it tells me to click on the same non-saturated star. So I can pick somebody like this guy over here, the fine star. Click on this. Loads up again. This is now the next frame. It's circled it. It says, hey, I think this is your star. And am I right? On the bottom, it says, OK, look, if you click Shift and then click on it, you're going to skip this one. Command, it'll then say keep this guess, or Alt, click, and it'll automatically do all of them. And that's the right one, so I could hold down the Command on my Mac keyboard. On the it's Control on a Windows keyboard, so I can just go through here and I can just say yeah, that's it, that's it, that's it. I could go through and I could say do all of them, but hey, look at this. This is one I hadn't flagged before as being bad, and yet it's pretty horrible. Clearly something happened to my tracking. You can see these little dashed lines instead of the stars. So this is a bad one. OK, well, I could do this little shift thing to say skip it. Or I could click over here and say, you know what? I want to skip this one. This is telling me I've selected one star in each one of these so far. And this is now saying I've skipped this one. I could move on to the next one. Say, yes, in fact, that's my the one I want to use. You can also now tell Nebulosity, hey, look, I really, really like, I want everything lined up with frame number 1. Have this guy be the reference. You can go through and say that, yes, in fact, this one here should be the one that gets locked into for everything. OK, so we can go through and we can do that. That's handy when you're doing things like LRGB and you want them all to line up on top of each other. But I can come through here and I can say, yes, in fact, that's my star. And I can then say, OK, yeah, let me hit that command to keep the guess here. And then let me just tell for the rest of these here, because I know my tracking is good, automatically go to all of them. I'm not used to this running so slowly, this Google Talk plugin. Slowing it down. OK, it's giving you a little readout as to how many it had to go there. It's now going through, and it's actually doing the registration, figuring out how much it needs to shift each one to get it to line up, and then it's saving it as a line underbar HISTEM, underbar preprocess. So for every file that Nebulosity makes, you then get to know really sort of what its history was here, because it's telling you all of the stages that it's actually done on it. It makes for beastly long file names, but I'd rather know what happened than have to just be guessing and hope I come up with a reasonable convention myself. OK, so now it's gone through, it's done, it's finished these. It also makes a little text file that, by the way, tells you everything it had to actually do to the alignment, that it was skipping this one, that it used 1 star, how much it shifted, and all this kind of thing. Handy sometimes. And now it's gone through and it's done this. Now, I split it out into these 2 steps because I wanted to be able to show you all that you also now have another sort of option here. When you're not doing any alignment, when everything is all set here, you can now also say, well, you've been able to do this for a while, but you can say, all right, I want you to be a little bit cooler when you're averaging these things together. Instead of just taking the average or the mean, I want you to be able to do some standard deviation or sigma kind of clipping on it. I give you standard values you can choose from, and if you really want, you can also pick a custom one. All right. Now, I could go through and I can run this kind of thing, but first, let me try to give you an idea as to what the heck this actually means. What is standard deviation-based combining, and why should we care about it? All right, if I do this, you can now see it?
Yep.
All right. So then, I've said already, remember that whole thing with me lying about how much was in my wallet? Sometimes I might say 10, sometimes I might say 15, sometimes I might say 12. If you were to plot all of, if you were to take 100 samples of this, you can make a histogram of my responses. And they would have averaged on 13. The mean would have been 13, and there would have been some good number of them that were, well, pretty close to 13, like 12 and maybe 11 and 14 and 15. There would have been some of them where I said 17. I might have even said $18 every once in a while. And who knows, every once in a while, I might have said $5,000, man. OK, so if I looked at the histogram here, there would have been a nice distribution, but then sitting outside that nice distribution, there would have been some extra little values we call outliers. On a normal distribution like this, and your CCD data should be a pretty normal distribution, on a normal distribution, there's a neat little rule. 68% of your samples are within 1 standard deviation. 95% are within 2 standard deviations. 99.7% are within 3 standard deviations. So in a normal kind of thing, if there aren't any outliers, 99.7 of them are within 3 standard deviations, 95% are within 2, and 68% are within 1. So OK, so I pick as standard kind of things, 1 or 1.5 standard deviations. So we're saying that these things out here, we're going to throw them away, because we think that they're probably not actually representative. Here's another way to look at it over on the right. On the right, I have, OK, just some faked kind of data here where I said, OK, look, I took 1, 2, 3, 4, 5, 6, 7 or so samples, 7 or so images, and then these might be 2 different pixels, pixel on the left and a pixel on the right, and here are the values of my different samples. So in this pixel here, it's darker than the one next to it, and you can see there's a nice little clustering here, and then there's this one guy standing out there. I could take all these guys here, nice little clustering, and there's this one guy standing out here. If I were to take the average of all of these pixels, it would end up being about here. It would get skewed by this outlier. We want a way to be able to throw away these outliers. Now, if you take a median, that's one way of throwing them out. But this sigma clip is an even better way of doing it. It figures out what the standard deviation is, and then figures out ones that are more than X number of standard deviations away, and it throws those away. Now, this standard deviation-based clip comes in really, really handy for you. Let me actually just load up right now in the preview some that I'd already run to give you an idea as to what this can actually do. I'll load up this 1.5 and this red average. I'll load them all up. OK, so this is data from the red filter. And on the red filter, I showed you before, as we were going through and we were looking at the that initial kind of just go through the pass-through with the preview tool, you saw that there was that plane. All right? And so if I now go and I take a look at actually the average, see right here? There's this line. Let me see if I can make it a little bit clearer for folks. All right. See right here, right here, and right here? That's the plane. Here we go. In the average, of course, the plane is, well, those are images. That's an image just like every other. And here's this, there's a very, very faint thing I can pick out on my screen. You won't be able to pick it out on yours. There's the very faint line of the satellite there. And as I would start to stretch it, these would become more and more apparent. So this then is the plane coming through and, oops, all right. If I ever go and I say, all right, let's look at one of these sigma combines, it's gone. The plane is completely gone. The satellite's gone, the plane's gone. In fact, in this one here, I included also one that had some poor tracking. With the poor tracking, we could also end up seeing that that would come through faintly in the image, as you 1 out of 20 of your images here had a real issue. But hey, you know what? For those pixels that are right next to the star, everybody else says it's dark. It's only that one that says that it's really nice and bright. When you do the standard deviation kind of combine, it throws away that image in the stacking for that pixel, and so it only combines 19 instead of 20 of them, and hey, you end up with a nice clean image right there. All right, so by doing that standard deviation or sigma clip kind of combined, we can go through and we can reject out cosmic rays, planes, satellites, poor tracking in individual images. If you have poor tracking in all of them, it's not going to help you in the slightest, but if you have poor tracking in just some of them, it's going to pull those away. It not only pulls out bright things, it pulls out dark things. If for some reason you had a black pixel right there, all right, it'll pull that out as well, so long as it doesn't line up across your images. This is one of the huge reasons why people like to dither across their frames, so that as you actually take your images, the stars move relative to the hot pixels or other imperfections. That then gives this standard deviation-based combining a fantastic shot at being able to actually then go pull out the hot pixels, because the hot pixels are then moving. Once you've lined things up, the hot pixels move from frame to frame. The stars are still, and the hot pixels move. So they then easily become outliers. So that's another technique that people who have things like digital SLRs often use. They try to get a good amount of dither moving between the frames. That gets it so the hot pixels and warm pixels don't line up. That also gets it so that the fixed pattern noise doesn't line up. So again, you can get things like a sigma clip combined or even just averaging to be able to pull out those kinds of problems. All right, so then at this point here, we now have something that is ready to go through and ready to stretch. And we're now out of any kind of thing having to do with the land of pre-processing. And so you can go and you can do things like your standard kind of levels tools. You can go and do things like, oh, I hadn't realized I had a little selection active. Let's not have a selection active and go and do the levels tool. I was wondering why it didn't seem as if it was actually doing anything. You can now go and do all your standard processing of levels and curves. You could take things into another program if you want, whatever you like. You could then be starting to try to actually pull out the cool stuff in your data. So at this point, questions that people are actually having, though, about pre-processing theory, pre-processing in practice, anything else having to do with PhD, nebulosity, signal to noise, any of these other kinds of things? I'll open it up.
You guys are all having perfect results, right?
Well, I think that was a terrific exposition. It's hard to even have a question.
How would you determine, which, like for which standard deviation you would use? You've got 5 or 6 different options there. How do you determine which one you want?
Empirically is really the answer. So go through and, so my first pass and everything is 1.5 standard deviations. It's a pretty reasonable job at being able to pull things out. In fact, in science, in my publications on brain imaging or on behavioral data or anything, certainly going through and filtering at 2 standard deviations is kind of the norm. It's perfectly acceptable to filter at 1.5 standard deviations and nobody complains. If that's still not pulling something out, some frame you really want to keep in, and it's not pulling it out, tighten it up. Take it down to 1.25 or something like that and see if you can get that to go away. As you cut down the standard deviation threshold, you're letting fewer and fewer of your frames through. And by doing that, you're then getting, in many ways, a noisier and noisier sample. So it's a balance that you need to play here, and it comes down entirely to what your data and your noise actually looks like. So I always start with 1.5, which is, again, why that's one of the defaults there and labeled typical.
Okay.
Can I ask a PhD question?
Sure.
So I think when you do the calibration, it's I think creating a backlash.
Yes.
What it does, actually.
Okay. So by the way, quick plug here. If you can read code at all of the code for PhD is actually up on the web. If you can code and you want to actually have to write PhD, that's up on the web and everything as well. In fact, the PhD 2 effort, I donated the PhD 1 code, and other people have been taking the ball with it and running with it from there to be able to add in all of the cool things that are now in PhD 2, and I thank them profusely for it because I didn't have time to do it. But what I can then say is I can absolutely guarantee this is how PhD 1 works, and I'm 98% sure it's how PhD 2 works. So what it does is you say, okay, look, we first go east. It turns on the right ascension motor, goes east, steps you along, and it's counting up how many steps that it actually does. It then dials those same number of steps back and gets you to pretty much the starting position. However, when it comes to, because in right ascension you do not have to worry about backlash. When you are guiding, as long as you don't have wind that is knocking you back and forth in the gears, you never, ever, ever reverse the direction of the motor, and so you never have to worry about backlash. You do have to worry about backlash in declination. Because declination, your drift is going to be in one direction, but as we're going and we're moving north and we're moving south here, we're actually reversing the direction of the motors. In RA, you accelerate the motor or you stop it, but in DEC, you turn it one way, you turn it the other way. So right before RA, we figure out where the star is, we go this way, we go this way, and we figured out what the distance was and what the angle was between the original start position and here. At that point, when it's come back and it says it's now going north, it says clearing the backlash, it turns on the motor going north, and it starts looking and saying, has it moved yet? Has it moved yet? Has it moved yet? Has it moved yet? Oh, it's moved. There's a built-in little threshold to say, oh, the star has now moved. And once it's done that, it re-zeros internally the lock position, and now it starts letting it actually go north. Once it's calculated out that number of steps, it runs those same number of steps backwards, and the reason why it ends up in a different spot is because that is the amount of backlash that you have in your declination assembly. Now in PhD 2, you can tell it, no, I'm sorry, I actually want to go back there. The default is to leave it still, though, where it was before. But that distance is exactly your declination backlash. There is a gotcha in this mechanism if you are poorly polar aligned, or if you have a really, really, really crummy mount. So let's say you're going this way, dun, 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 and you go back. But in all of this, you actually have either a whole bunch of drift, or you have periodic error that is going like crazy. So let's say that your star is just doing this because of massive periodic error. Now, when I say go north and clear the backlash, well, okay, I try going, but I'm still in the backlash, but hey, periodic error threw me way over. It's going to think that distance there was clearing the backlash. If your mount is that bad, I can't help you. Get a better mount.
Get a new mount. Hey, Greg.
Folks at OPT and other folks, other places will thank me for that.
Craig, I've got another PhD question.
Yeah.
Or issue maybe. I've got let me describe the configuration. It's a 10-inch bead, LX200.
Mm-hmm.
Got a ST8300 camera, and one of their filter wheels, and then the OAG 8300 off-axis guider.
Yeah.
With the SDI camera.
Mm-hmm.
Okay, and PhD seems to guide nicely when I have 6.3 focal reducer on it. So it reduces it from f10 to 6.3.
Mm-hmm.
When I take the focal reducer out, as far as I can tell, I haven't changed anything else. I haven't been able to get the PhD to give me reasonable results.
Right.
It's just
So so now you have a 10-inch system running at f10, right? So you're at 2,500 millimeter focal length.
That's the camera. Actually, the OAG reduces it by 0.7, so it's like.
Sure, but when we're talking about, but let's for the moment right now think about what's actually going into your main image, because that's where you care about the tracking. You want to be able to have your main image have a nice result there, right? All right. So the magic formula is 206.265 times your focal length divided by it's a 5.4 millimeter 5.4 micron pixel, I believe. Is that it? Sorry. Times 5.4 divided by.
On the ST8300, yes.
Yeah. So what this means is that you are running at 0.44 arc seconds per pixel.
Right.
All right. Why are you running at 0.44 arc seconds a pixel?
Why am I doing that?
That then is actually my initial answer to this, because in our skies here, unless you are up, there are a couple of spots in Southern California.
2 arc seconds, by the way.
Excuse me? Excuse me, I didn't hear that.
The average seeing that in my Poway backyard is about 2 arc seconds or so.
Exactly. So I was going to say, our typical kind of seeing on a good night in a good place is about 2 arc seconds. I'm often around 3 and all this kind of thing, and fine. So you are a bit oversampled. And so what we're getting in all of this here, we've got to, of course, remember is that you're going to be having seeing effects that are going to be entering into this as well. And you're trying to have the mount go through and correct for some of this. Now, when we're talking, 1 second exposures, you filtered out some amount of the seeing, but you certainly haven't filtered it all out. And so you're getting to magnify the problems in terms of the guiding. A real interesting question is going to be whether the guiding is actually, in truth, any worse when you're running at f10, or whether you've just effectively blown it up so much that it looks a heck of a lot worse.
Yeah, my judgment is that it is maybe a factor or two worse, taking account of the fact that I've blown it up.
Right, right. So then if you take the blown up image, and here's the key, you reduce that down to the other one, does it, if you do it that way instead of blowing up, the question then is at that point, do they actually look roughly the same, or do they look much different? Now, when it comes to trying to dial things in at higher focal lengths, you do have to start then thinking about, okay, first off in my calibration here, how far am I actually having it go through in the calibration? All right, let me try to have it go maybe a little bit further in the calibration so that I don't have the same step size quantization error I might have. So you don't want it to calibrate in 1 or 2 steps. Is it still taking 20 or so steps to actually do it?
So you use smaller calibration step size.
Exactly. You use a smaller calibration step size to then try to figure any of these kinds of things out. You then also start having to work a lot more in terms of saying, okay, let's think about things like the hysteresis and the other kinds of algorithms that we use to try to figure out what's going on. Because that poor little guide chip now has everything that's been blown up a whole bunch more and doesn't have, it's getting more of the seeing effects and all this kind of thing. So you're having to fight a little bit more to factor those kinds of things out. Yeah. My answer is I don't image at f10.
Yeah.
There's another reason and a whole nother talk as to why I don't image at f10, and that has to do with your signal to noise.
Yeah.
Your DSO signal to noise is so driven by the F ratio, it's ridiculous. And so the more you can do to pull that down and pull that down and pull that down, the better and better off you are.
Yeah.
So, yeah. But in any case, in the end, I haven't had a whole heck of a lot of experience guiding at F10 to try to dial that in. The first thing I tell people to do when they've gone and bought their SCT, they're like, yeah, I got a whole new setup for the SCT. I want to start taking images. I haven't done it before. Please go spend $150 or whatever and buy that reducer, because your life is going to be a heck of a lot easier. Yeah. If you can hook up an adaptive optics rig, that is going to make your life a whole heck of a lot easier when you're doing long focal length kind of imaging. A whole lot easier.
Question on the number of bias flats and darks. I typically do 20 10-minute subs per filter. So how many darks, flats, biases would be best?
So is yours a cooled camera, a regulated cooled camera?
Yeah, it's a QSI.
Perfect. A lot, because you might as well. I mean, you can set the camera up on your desk, indoors, and say, go take 500 bias frames. Go take 1,000. I don't care. It's going to take you an hour or something like that. Fine. It doesn't matter. You can delete them all at the end once you've stacked them. And that then goes into your library. And same thing with the darks. Set it up on indoors in your desk, set it to cool at your -10 or whatever you can get it to or whatever, and go take 50 of them. Go take 100 of them. In a lot of my libraries, they're not 50 or 100, they're more like 40 or something like this. But realizing that any bit of noise still in there is going to be injected into your images as you're doing your calibration. And if it just means plugging it in and walking away for the day, plug it in and walk away for the day. Realize also, however, that this is going to go follow a 1/√number of frames kind of function. In fact, I can call that up for you guys, or can I? Don't know that I can call that up for you right now. But in any case, it's a curvilinear function that just goes and has a function like this, and sort of drawing it out with my mouse. And so what that means is that as you go through and you add more and more images to it, you reach a point of diminishing returns. You can actually sort of see something that's sort of like it in the side of this bell curve here. It's much steeper, however, initially.
You share your desktop first to see it.
Yeah. So oh, sorry, of course I would have needed to have given the desktop there. In any case, it's a curvilinear function like this. I'll do like that. How about that? So if you're looking at the difference between 50 and 55 or 50 and 60 frames, there's not a whole heck of a lot of difference. It's a percentage of what you've actually had in your stack there. The difference between 1 frame and 10 frames is a monstrous difference. The difference between 10 and 100 is a monstrous difference. The difference between stacking 95 frames and 100 frames doesn't matter in the slightest.
Craig, this is Dave. Interesting. I talked to Tony Hallis at the imaging conference just after he spoke. He did an article in Astronomy called Chasing the Curve. Mm-hmm. And it's his opinion that anything beyond 15 is a waste of time because the asymptotic curve that occurs much beyond 15 flats or darks or whatever it happens to be. He says the curve, the change in the curve over the amount of frames is so minor that beyond 15 you're wasting your time.
Yeah, so in fact, let me see here now if I can call up that, because I just, in that talk, I had this curve. And I don't use 15 as my sort of cutoff. I'll do 20, 30, a decent amount, and I'll try to show you if I can. Here we go, the PDF of this.
You could always go with the analogy that it takes 30 to be statistically significant. How's that?
There we go. Tell you what, now let me go over to the sharing here, and let me share this. Okay. So these are slides from that talk that he was talking about here. All right, so here we go. Here's the noise in the stack as a function of the number of images. This is just your 1/√n. So can you see my pointer?
Oh, yeah.
Okay, good. So this is then 5, this is 10, this is 15, All right, so yeah, you've gotten now the lion's share of the curve, but 20, 25, 30, you've dropped some more. It's still going down. Now, beyond about 30, so if we say, okay, look, let's figure out how much it takes to do, as you're going, how much does it take to do a drop of 1 unit here? And we can say, all right, look, and you're in the initial portion of the curve, you're dropping in, 1 sample here. You've gone from way up here to way down here. And then the next one, still in 1 sample, you've gone 3 or so here. And then over here, by the time we're at 3 frames, we've dropped basically 1 unit. Now, by the time you're over 5, 10, 15 here, to go down and get 1 more unit, you're talking another 5, 10, about 15 or so frames, getting you out to 30. This is 1 over root 2. It's going to be a doubling kind of thing. But then to get from here to dropping another one, well, we've got to add then another 60 frames. So this is why he says, okay, hey, look, stopping around 15 isn't a bad thing. But it's only not a bad thing if time actually matters. And there are times in which time matters. There certainly are times in which time matters. When I'm taking, my flats, okay, I'm taking them in the morning and this kind of thing, but they go quickly, and so, okay, I can easily grab 20 or 30 of them. When I'm taking, if I have to take darks that same time, all right, then it's going to matter. But if you have a cooled camera and it's nice and stable, set it up sometime during the day and just take a bunch of them, and it's not a problem. You do get a return. It's a point of diminishing returns, but you do get a return, and there's no cost to it. The only cost to it is maybe some hard drive space if you decide to save them. But you can always drag them to the trash or recycle bin, and then why not? So that's why he says 15, but that's also why I say you might as well grab some more.
Does Nebulosity ever reach a point where it can't handle 10,000 frames or something? I mean, is there a limit to it?
No, there should be absolutely no limit to it. As it's going and doing things like stacking and pre-processing, what it's doing is it's building up an accumulator. So it has a 64-bit float image that it's keeping as an accumulator, a double precision float. It loads up an image, 32-bit float, copies it into theirs or adds it into this one, drops this memory, loads the next frame in, adds it in. So the memory footprint is constant whether you pass in 2 images or 200,000 images. It just takes more time. But as maybe once a year.
You want to introduce us to your family?
Yeah, you keep seeing some of them walking past there. So you initially saw on the setup my older son, Gavin. You saw a little fleeting, oh, actually, no, you saw my younger son stand here and stare at you for a minute or so. That was Miles. And then you just saw my my wife walk by there as well, who's now, I think, going to be self-conscious about walking past by here again.
How often do you think you should redo your darks and your flats and things like that?
Yeah, so Kevin at QSI did a nice little explication of this at one point, in that your sensor does change over time. As it gets hit by cosmic rays, the hot pixels will change. You'll create hot pixels, you'll create warm pixels. Cosmic rays can do that. And so, for me, if it's been more than, call it 6 months or something like that, I'll probably generate a new library. I'll say I do that. I let it typically go a heck of a lot longer, because the damage in all of this, let's say I have some new hot pixel. Well, if I actually have some nice dither between my frames and I do a standard aviation kind of combine, the hot pixel goes away anyway. All right? Let's say there wasn't enough dither between the frames and I have a hot pixel right there. I take the Photoshop heal tool and I go, and it's gone. Okay, that wasn't so bad. So as long as I don't have a huge number of them, it's not a huge kind of problem. In terms of Kevin's recommendation, if I remember, it was every 6 months to a year or something like that, just remake your library. I haven't shopped for a good long time, so I'm going to make a new library.
Yeah. What if you make a change to your optical train? Do you want to redo everything at that point?
Nope. Because your biases and your darks don't care in the slightest about your optical train. Your flats do care, and the one thing I take every single time is I take flats every single time.
Okay.
Because I can't guarantee that the dust spots will be exactly the same. And if you remember, you are dividing by that flat, so that is having a massive effect on it. And so if you got dark in your flat and you're dividing, you can think of that as multiplying by brightening. It's the same math, and so if that's the way you think about it here, all right, hey, look, if that's shifted, if there's a new one or something like that, you're going to get a nice big spot right on there. And again, as my filter wheel goes along, chunk, chunk, if there's dust on the filter wheel and it doesn't end up within 7.4 microns of where it had been before, the size of my pixels, it's not going to line up the same. So okay, I go and I take my my flats. Now that said, I don't take the flats exactly as I've taken them. I do take them the next day, but as the camera gets jostled around or who knows what, I take them each time.
Okay.
So, I mean, look, if you get away without taking them each time, great, let me know. But I've always sort of felt that I should take them each time. I have a little electroluminescent panel I just stick on the top of the telescope. I have a little script I run in Nebulosity to go and automate the capture of them all. It just goes through while I'm going and packing up the rest of the gear, and then I pack it up and I go home.
Greg, can I ask like CCD camera question? I read your QHY10 nice review about it.
Yeah. Mm-hmm.
And then it looks like, yeah, the review was great. And then just we'd like to know, like, in the quality of the product-wise, is this QHY making a good quality of product?
You know, they really are. It's not of the same, sort of fit and finish that you get on something like my QSI. I've had cameras from a lot of manufacturers here, and a number of them make really, really just well put together pieces of machinery. And I do love my QSI on that. I'd say that the QHY doesn't have quite that same level of polish, but it's got it where it counts. And it really, really was a nice camera. I was very, very pleasantly surprised with the quality of the noise, sort of how smooth the noise actually was on the camera. The much older QHYs I'd tested, they would have some salt and pepper noise, but he's really gotten his electronics worked out nicely to be able to have that. The issue in the QHY, the nice thing is that the camera head itself is, of course, pretty nice and small. In fact, here it is. Here's the QHY10.
Mm-hmm.
Yeah, I have an insane number of cameras basically at my fingertips right now. There are lots of cameras at my fingertips right now. If we really wanted and you could let me go downstairs, I could grab another dozen. So if anybody's ever looking to break in somewhere and get themselves a new camera, don't come to my house, please. But in any case, the nice thing about it, I mean, it's great in this is a nice small package, so it doesn't weigh a whole heck of a lot. If you want to do something like hyperstar imaging or that brand new Celestron, I forget what the heck they call it, but it's that really cool new design, that something-something camera. In any case, this goes and can be right on the central obstruction perfectly well. It doesn't put a huge amount of weight on there to torque your focuser or anything. But at the same time, it then means that it needs an extra little box to be able to actually handle the some of the electronics and cooling. The other drawback is that it draws about 4 times the amount of current that my QSI camera draws, and it's loud. So it goes but all right. But then again, it's a nice big sensor here. See if we can get that nice big APS size sensor, fully cooled, one-shot color camera. For some reason, they stick a guide port on here too, because if you use this as a guider, I'm going to smack you. But in any case, it's otherwise a really, really nice camera. They even have controls inside here to be able to adjust the optical plane, because the CCD may not actually be exactly perpendicular to like the faceplate and the threads, and so now they have a nice system here to be able to adjust that, to be able to recharge your desiccant, all sorts of nice stuff now built into this. So I keep kind of threatening and thinking that, okay, look, I've got a 10-inch carbon fiber Hyperstar capable SCT, and I could drop, what is it, about $800 or whatever, and get a Hyperstar setup on it and stick this right in front and be imaging at f2. And that would be nice. I keep threatening, and then I stick with my 4-inch f4 Borg, which I also love, and stick with the QSI on there. Although for travel kind of stuff, I may end up taking this. I don't know. The 4-amp draw that you need on the current is a bit of a limitation there, though. Sucks down. If you're running on battery power, that's the only time I'd really sort of worry about that.
Have you ever compared with the 12 with 10?
Yeah, so the 10 and 12, electronic-wise, they're identical. Control-wise, they're identical. This actual CCD is a little bit different, and so it's a difference in terms of the pixel size and the megapixel count. I haven't actually had a 12 here, since the coding on the 10 was the same as on the 12. A dealer did a test on the 12 for me. I do have the 8 Pro in one of these drawers over here. I think it's the thing behind me, and the headphones won't reach. In any case, that's a slightly different camera in terms of its electronics and readout kind of thing, but the pixels are even a little bit bigger. That was also, I tested that one. It was also a really, really nice camera. I was very impressed with both of them. I've been impressed, actually, these days with a number of different camera manufacturers. I can speak directly to the ATICs that I've tested and the Starlight Expresses that I've tested, and they've got some really, really nice smooth electronics now. The ATIC that I tested several years or so ago now, but oh man, that was a very, very smooth, clean electronics, and I really like the Starlight Express H9 I had here as well. I'm not mentioning apogees and FLIs and SBIGs because I haven't had them here to test a whole heck of a lot. I did have had an apogee here once. I ran it through. It looked nice, but it's this big and it weighs about 10 pounds, and so I couldn't even mount it onto my telescope.
Thank you.
Anything else? Great. Well, thank you very much, Craig. That was excellent.
Well, you're very welcome.
At this point in time, I'll hit the button that says stop.
Craig, what do you drink and where do we send it?